Good morning. Now I am going to give seminar on electrometer and transimpedance amplifiers. I am Saicharan. I am from VIT University pursuing my MTech. Coming to the contents, introduction. What is the electrometer and types of electrometer? What is transimpedance and its operations? What is an electrometer actually? Electrometer is an electrical instrument for measuring electrical charge or potential or electrical potential difference. There are many types of electrometers. They are ranging from historical handmade mechanical instruments to high precision electronic devices. Modern electrometers based on vacuum tube or solid state technology can be used to make voltage and charge measurements with very low leakage currents down to 1 femtoampere, that is very less amperes of current can be measured. A simpler but related instrument, the electroscope, works on the similar principle but only indicates the relative magnitudes of the charge. And coming to the types of electrometers, we are going to discuss now gold leaf electrometer. Gold leaf electrometer was one of the first sensitive instruments used to indicate electrical charge. It is still used for science demonstrations but has been suppressed in the most applications by electronic measuring instruments. The instrument consists of two thin leaves of gold foil, electronic measurements suspended from an electrode. When electrode is charged by the induction or by contact, the leaves acquire similar electrical charges. Here the leaves are which are coated in yellow color and given in the opposite directions of movement, which when the electrode is charged by the induction or by contact, the leaves suspend from an electrode. When the electrode is charged by induction, that is when induction heating is given to the leaves, they will be discharged from one place to the other and each other repel due to the Coulomb force. Their separation is direct indication of net charge stored on them. On the glass opposite the leaves, that is the surrounding globe shaped glass, on them the leaves are diverged fully, they may discharge into the ground. The leaves may be enclosed in a glass envelope to protect them from draughts, and the envelope may be evacuated to minimize charge leakage. A further cause of the charge leakage is ionizing radiation be evacuated to minimize the charge leakage. So to prevent this phenomena, we use the electrometer. Electrometer is surrounded by a lead shielding. This principle has been used to detect ionizing radiation. As seen in the quartz fiber electrometer and Kearney fallout meter, this type of electroscope usually acts as an indicator and not as a measuring device. Although it can be calibrated, the bronze electroscope replaced the gold leaf electroscope for more accurate measurements. The instrument was developed in almost 18th century, and now we can discuss on the other type of electrometer, that is early quadrant electrometer. Early quadrant electrometer is a device which is used with the term quadrant electrometer, eventually referred to Kelvin's version. This term was first used to describe a simpler device. It consists of an upright stem of wood to which affixed to a semicircle of ivory. That is, to this stem, a semicircle is connected which is affixed to that. From the center there hangs a light cork ball upon a pivot. When the instrument is placed upon the charge body, the system participates and repels the cork ball. The amount of repulsion may be read off the graduated semicircle this direction, though it is obvious that the measured angle is not in the direct proportion to the charge. And coming to this, This design uses torsion to give measurement more sensitive than repulsion of the gold leaves or cork balls. It consists of glass cylinder with a glass tube on the top. The diagram is given here. Glass tube on the top. In the axis of the tube is a glass thread. The lower end of this holds a bar of gum lac with a gilt pith ball. That is, these are the small balls which are called as gilt pith balls at each extremity. Through another aperture on the cylinder, another gum lac rod with gilt balls may be introduced. This is called carrier rod. If the lower ball of the carrier rod is charged, when it is entered into the aperture, this will repel one of the movable balls inside. All index and scale is attached to the top of the glass rod. The number of degrees twisted here shown in the figure to bring the balls back together is an exact proportion on the amount of charge of the ball of the carrier rod. And coming to this is the diagram where these are the balls which are connected to the rod. And coming to the Kevin's quadrant electrometer, which is developed by Lord Kelvin. This is the most sensitive and accurate of all mechanical electrometers. The original design uses a light aluminum sector suspended inside a drum cut into the 4 segments. These segments are insulated and connected diagonally in parts. The charged aluminum sector, this part of the aluminum sector, is attracted to one pair of the segments and repelled from the other. The deflection is observed by a beam of light reflected from a small mirror attached to the sector, just as a galvanometer. The engraving on the right shows a slight difference from this electrometer using 4 flat plates. They are rather than closed segments. The plates can be connected externally in the conventional diagonal way, that is in this way and this way, or in a different order for specific application. Coming to this is the diagram. Coming to the solid state electrometers, this is which is one of the most advanced modern electrometer. And one of the most modern electrometer is the solid state electrometer. The most modern electrometers consist of solid state amplifier using one or more field effect transistors, connections for the external measurement devices, and usually a display and a data logging connections. And here the amplifier amplifies the small current so that they are more easily measured. The external connections are usually of the coaxial or triaxial design. And now coming to these are connected diodes or ionization chambers for ionizing the radiation measurement. Solid state electrometers are often multi-purpose devices that can be used to measure voltage, charge, and resistance and current. They measure voltage by means of voltage balancing, in which input voltage is compared with an internal reference voltage using an electronic circuit with a very high input impedance of about 10 power 14 ohms. A similar circuit modified to act as a current to voltage converter enables the instrument to measure the currents as small as a few femtometers. Combined with an internal voltage source, the current measuring mode can be adapted so that the very high resistance of order 10 power 17 ohms can also be measured by using this instrument. Finally, by the calculation from the known capacitances or the electrometer in input terminal, the instrument can measure very small electrical charges down to the small fraction of picocoulombs. And now comes the transimpedance. Transimpedance amplifier, which is known as TIA, is current to voltage converter, most often implemented using an operational amplifier. The TIA can be used to amplify up to the current output of Mueller tubes and photomultiplier tubes and accelerometer, photo detectors, and other types of the sensors. Current to voltage converters are used with sensors that have a current response that is more linear than the voltage sources. This is the case with photodiodes, where it is not uncommon for the current response to have better than 1% linearity over a wide range of light input. The transimpedance amplifier presents a low impedance to the transimpedance amplifier as a just large valued feedback resistor. The RF gain. The gain of the amplifier is set by the resistor because the amplifier is an inverting configuration, that is, which has a value of minus RF. There are several different configurations of transimpedance amplifiers, each is suited to a particular application. The one factor they all have in common is requirement to convert the low level application. The one factor they have that is the gain, bandwidth, as well as current, voltage, and offset change with the different types of sensors, requiring different configurations of transimpedance amplifier. And coming to the operation, here we can give the operations of the transimpedance amplifiers. In this, here the circuit is given in a way that to represent the transimpedance. In the circuit which is given in the figure 1, the photodiode is connected between the ground and the inverting output of the op amp. The output of the input, the other input of the op amp is also connected to the ground. This provides a low impedance load for the photodiode, which keeps the photodiode voltage low. The photodiode is operating in photovoltaic mode, which has no external bias. The gain of the photo amp gives the photodiode current equal to feedback current through the feedback resistance RF. The input offset voltage is due to photodiode and is very low in this self-biased photovoltaic mode. This permits a large gain without any large output offset voltage. This configuration is used within the photodiodes that are illuminated with low light and require a lot of gain. And coming to the frequency and the bandwidth and stability, the frequency response of the transimpedance amplifier is inversely proportional to the feedback resistance. The product of the gain V input to the V output is very close to being a constant for any given op amp. The sensors that transimpedance amplifiers are used with usually have more capacitance than the op amp can handle. That is, in this figure 3, the models, the sensors as a current source, the sensor as a current source and capacitor. The capacitance across the input terminals of the op amp, which includes internal capacitance of the op amp, introduces a low pass filter in the feedback path. The low pass filter can represent that response of the filter can be characterized by using the feedback factor, that is beta, which attenuates the feedback signal. This places a greater demand on the amplifier gain. And now coming to the at low frequency feedback, factor P has an varying change. The amplifier response will be close to ideal. Coming here, V output beta is equal to XCI by reference voltage, reference resistance plus XCA, that is, which is equal to 1 by 1 plus RF into capacitance CA. V output is given as input power, input current to feedback resistance plus 1 by AOL of beta. And coming to the uncompensated transimpedance amplifier, FZF, that is 1 by 2 pi RF into CI plus CF, that is the capacitance values are given, which is given in a graph. This graph is plotted between the given values of the gain and the frequency, and FCF is 1 by 2 pi R into CF. Beta is equal to 1 plus RF into CFS plus 1 by RF into CI plus CF into S. And for this the compensated transimpedance amplifier and then normal transimpedance amplifier, there is a great change in that. That is, the compensated feedback factor plotted as a reciprocal 1 by beta starts to roll off before Fy, reducing the slope at the intercept. This is the intercept. The loop gain is still unity, but total phase shift is not full 360 degrees. One of the requirements for oscillation is eliminated with the addition of compensation capacitor. So the circuit has more stability than without the compensation capacitor. This also reduces the gain peaking. Producing a flatter overall response. There are several methods to calculate the compensation capacitor's value. Compensation capacitor has too large value will reduce the bandwidth. Bandwidth is given in this. The bandwidth of the amplifier. If the capacitor is too small, oscillation may occur. One difficulty with this method of phase compensation is resulting small value of capacitor, and iterative methods often required to optimize the value. There is no cut and dry formula for calculating the capacitor value that works for all the cases. Here, the compensation method plays a major role in transimpedance amplifier, which uses larger value of capacitor that is not susceptible to parasitic capacitance effects, which can also be used. And from this, we can say that the capacitance of the resistance of very high ohms can be measured using these electrometers, and by using the capacitors we can reduce the work so that we can measure the current values very easily. Thank you.